In this video, we'll discuss writing Verilog programs to simulate binary adders. Example 4.2 of your textbook. We'll start from the half adder. In the class, we discussed that a half adder has two inputs and two outputs as shown in this diagram. Now in this figure, A, B are the inputs, sum and carry are the outputs. Sum here is equal to A exclusive or B. Carry is equal to A and B. So we want to implement this half adder. So suppose we call our program adder dot v. So to start, we write a module half adder module HA representing half adder, and we have output C representing carry, output S representing sum, and the inputs A and B. And so S will be equal to A exclusive or B, C will be equal to A and B. So we use this function exclusive for output S, inputs AB, and output C, inputs A, B. So this is our half adder. Let's compile to make sure we don't have any type of error. Okay, so there's no error. And we can use this half adder to build a full adder. Now, as we have discussed in class, a full adder can be built in this way, using two half adders and an OR gate. So a full adder has three inputs, A, B, and C in, the carry in, and two outputs, the carry out, and the sum S, and the relation is shown in this diagram. So we need to implement this function. I have written the module already. I just need to import it. So this is the full adder. I call it FA. Again, the output C, output S, representing the carry and sum, and three inputs A, B, C. So C here is our C in. And so we just create two half adders. So we instantiate two half adders, HA1, HA2, and we need four variables, C1, S1, C2, S2. C1, S1 basically is this C1, S1, and C2, S2 basically is this two outputs from this half adder. And so this S is equal to this S2, and C out is equal to C1 or C2. So as you can see, so A1 representing this half adder. So we have inputs AB, outputs C1S1, and A2 representing the other half adder. C2 is the output, S is our output, and C is the input, and then S1 is the input A. And then at the end, C out is C1 or C2. So that's what we have. C1 or C2 gives us C. And the other half adder gives us S. So these are our two outputs, S and C. So this implements our full adder. And again, we can check whether we have any typo errors. Okay, again, there's no error. So now we need to write a test bench to test this adder, full adder and half adder. So I've written that, and I call this adder tb.v. So this module adder tb is the test bench. We have inputs A, B, C, and these are the outputs. CH, the H represents half. Okay, so that means CH is the carry of half adder. SH is sum of half adder. F represents full. So CF is carry of full adder. SF is sum of full adder. So we instantiate a half adder. We call it unit under test, UUT. So CH attached to the port C of the half adder, SH attached to the port S, and A to A, B to B. So this is for testing half adder, and this UUT1 is for testing full adder. So CF is attached to the port C, SF is attached to port S of full adder, and A to A, B to B, C to C. And so A, B, C are our inputs. And for the half adder, we just need A, B. For full adder, we need all A, B, C. So we start with A, B, C equal to 0, and then we toggle it. For C, we toggle C. That means complement C every 10 time units. Here always only has one statement, so we do not need begin and end. Okay. And the same thing for the other one. So we toggle complement B every 20 time units, and A every 40 time units. Okay. As we discussed before, all these always statements are executed in parallel at the same time. So you can see that every 10 units we changes the C, the LSB, least significant bit, and B every 20 we changes B, every 40 we changes A. Okay. And then we display the input and output values, and we finish after 80 time units. So we can compile and execute this test bench. So we say iVerilog. We can say -O adder tb.v, and we need adder.v. So no error. And now we execute adder. You can see that we have this output as expected. So CH, SH are for testing half adder, and they depend only on AB. And indeed, say when 0 plus 0, we have carry 0, sum 0, and it is 0 plus 1, we have 0, 1. 1 plus 1, we get 1, 0. And for the full adder CF, SF, you can see that 0 plus 0 plus 0, we get 0, 0. And 0 plus 1 plus 0, we get carry 0, sum is 1. And when we have 0 plus 1 plus 1, we get carry 1, sum 0. And when we have A, B, C are all 1, then we have the carry 1, sum 1. So this is correct. Now we have also discussed that by combining full adders, we can build a 4-bit ripple carrier as shown in this diagram. So in this diagram, we have 4 full adders, and this we basically add 2 4-bit binary numbers, A and B. So here, in the first state, C sub 0, the input could be 0, and the bit A0 plus B0 gives us the sum S0, and it generates an output, a carry. This carry is added to the other stage, and the other 2 bits are added and gives us S1, and generates a carry added to the other stage, and again it gives us another bit S2 and generate another carry C3 output, and added to the last pair of bits A3, B3, and that gives us S3 and carry output C4. So to implement this, it is pretty straightforward. All we need is to create 4 instances of full adder. And again, I have written this, maybe we add this adder.v, add to here. So I call the 4-bit carry adder the module RCA4. So we have the output C4 here, and output C4, and output 4 bits of sum representing S0, representing S0, S1, S2, S3, and also the inputs A, B, each of them is 4 bits. A, you have A0, A1, A2, A3. B, you have B0, B1, B2, B3. And the input C sub 0. And C1, C2, C3 are intermediary variables. So they are not outputs. So the intermediate variable C1 will be the output of the first stage, and it goes to the input of the other stage, and C2 for the other stages, and so on for C3. So you can see that we create 4 instances of full adder FA for the first one S of FA sub 0 is this one. Now you can see that this So for this, we have the output C1, okay, C1 here, C1, and output S0, and input A0, input B0, and input C0. Okay. For the next stage, okay, now this is C1, which is the output from F of 0. Okay. We go into the input for the next stage, FA1 here. Okay. And then FA1 again, the other two inputs are A1, B1, A1, B1 here, and output S1, S1, and output C2. C2 will go to the next stage. Okay. So C2 goes to the FA2 here, as you can see, and then A2, B2, A2, B2, and the output is S2, S2 here, and C3 goes to the next stage, okay. C3 here, and B3, A3, and the output is S3, and C4 is the final output. Okay. So this is the implementation of the module for the 4-bit ripple carry adder. And so again, we can compile it, and so there's no error. So that means no typo error. And you should be able to write a test bench yourself. So it should look like this. So the module ripple TB, and we have the inputs AB, 4 bits each, and another input register C0. It is this C0, and then the outputs C4, this C4, and then the S or this S, and then you just do an instantiation of the RC A4. C4 goes to C4, S goes to port S, A goes to A, B goes to B, and then the display other values. And now try to write your own stimulus and initialization. So I believe you can do that yourself. Okay, thank you. Bye-bye.